Very good. So most of the work that I'm going to show is the combination of the work that some of my student has done, but this work has been integrated and now being continued by Abdelrahman Taha, who's my current PhD student. So let me get started by telling you what model updating is. So we as engineers, we are very well versed in developing physics-based and mechanics-based models, right? For the purpose of simulating the response of real-world systems, analysis, design, and so on. But if you had an opportunity to compare your model simulation with real-world responses, probably you have seen that there are a lot of discrepancies oftentimes. This is because our models depend on unknown parameters and input that we don't know oftentimes in prior. So the idea of model updating is that if you can go to your real-world structural system, for example, install some sensors on it, measure the response of that structural system, you can come back to your modeling domain and calibrate or update your model, basically. Train your model with the data, estimate the parameters, estimate even the input dynamics to the system, quantify the uncertainty, and have a trained physics-based or mechanics-based model. Now, this is what we call digital twin. Digital twin as a jargon has been overused in the literature, but what we refer to as digital twin is a trained physics-based or mechanics-based model with data. You can use that for what we call virtual sensing, which I will show you some stuff, diagnosis, prognosis, and the application to civil infrastructure is clear. It can be used for health monitoring, maintenance, decision-making, emergency response, and so on. But there are two problems within this process. The first problem is what we call modeling error. What is modeling error? So modeling error is all the simplification, idealization, or lack of physics that we have in our model, as inherent in all our models. And if we don't treat them, it will, through the model inversion, it will result in what we call biased estimation. And there is a theory on that and everything. The other problem is data, is that where should we put our sensor? What type of measurement we have to measure? Should we measure ground motion at the base of the building, at the foundation, or at the roof? Where will provide the most information to do this process? So the modeling error and data are two issues that will come back through this presentation. Almost more than a decade, I have been working since my PhD on this problem, and through the time we have developed, we have used the methods that was out there and improved it in order to be able to apply it to larger scale models in near real time. So the process that we are using for model updating, and excuse all the equation, but it's a Bayesian inference process, is that the unknown parameters, we're going to model them as random variables. The uncertainty of random variables will be characterized by probability distribution function. We're going to propagate this probability distribution function into our model. We're going to connect the stochastic outputs of our model with simulation, with measurements that we get out of our real world through what we call the simulation error model, which is very important. We're going to come back to it. And then once we have this simulation error model established, then we can basically update a posterior distribution of our parameter. And this can be done iteratively. Basically, as we're collecting more data or as data become available, we're going to train, and update the posterior distribution. This is a Bayesian inference that has been there for years. There's nothing new here. What we do in order to make this computationally efficient, applicable to large scale model, is that basically we use a first order approximation to propagate the uncertainties. If we do that first order approximation, then the maximum of posterior is basically the base equation will result in a very nice clean equation that we can use to update our parameters, the mean value of our parameters, and P is the covariance matrix of our parameters that quantify the uncertainties in our process. So this gives us a very streamlined process to do model updating. Now, in civil structure application, there is another big problem oftentimes we face, is that we cannot or we don't know inputs to the system. This happens, for example, when we have significant soil structure interaction. The foundation input motion, that basically those are the input motion that excites the soil, those cannot be measured really, or hardly measured. Or if we have like wind turbine structures, then you have a wind load and wave load that cannot really measure. We can guess them based on the stuff, but really we cannot measure them directly. So the problem of model updating, estimating parameters of a system, can be extended to jointly estimate the parameters and also the time history of unknown inputs. So these unknown inputs, we're going to treat them just as a set of parameters. Now our problem will be extended in the case that we're going to estimate the parameters of our system and the time history of our unknown input. So it's just an extension. We are dealing with a little bit bigger problem, but it's doable. Okay, so we have been applying this method to many different applications, including system identification of soil structure system. This is Millicon library for post-earthquake damage assessment of bridges and for operational monitoring of bridges. We also have done some work in offshore wind, basically in order to estimate the input loads on the offshore wind turbines. These input loads are very important because then we can use it for fatigue life estimation. And very recently, we are working on drivetrains of offshore wind turbines. We're trying to develop physics-based model of drivetrain, train them with data for the purpose of diagnosis and prognosis. And I have another trust going on wildfire, which we have the aspiration of doing similar thing with big, large-scale wildfire problems. It still hasn't happened, but we are continue working on it. So now to tell you a little bit of flavor of how this thing works, I'm going to just show you two examples very quickly, briefly, on the operational monitoring and on the wind turbine, and then I want to talk to you about modeling error and how we can deal with modeling error. So, very flash review. So bridges. We have, of course, a fleet of aging bridges. These bridges have problem with maintenance operation, right? Maintenance inspection. Post-earthquake is also a big problem. Right now, only applicable way that exists out there is manual inspection. And these are labor-intensive, costly, and not very accurate. So I'm not going to talk about post-earthquake assessment. We have done some work here. I'm going to talk about actually operational monitoring of bridges. Like as the bridges running, traffic is running on them, how can we come up with methods to estimate their situation and use them for decision-making, health monitoring, and so on. So we came up with a sci-fi type of thing idea, and this is more than 6 years ago. So the idea is that as the bridge traffic is traversing on the bridge, we have a system that we don't know the properties of the system, we don't know the loads, we don't know basically anything. So it's a very unknown system, very ill-conditioned system. But we can still crack the problem as vehicles are passing on the bridge using traffic cameras or other regular cameras like temporary cameras that I will show. We can use very common computer vision techniques to track the location of the vehicles on the bridge. That's doable, that's possible. What we don't know is the loads of this vehicle, and as the vehicle is moving, the load is also dynamic. So we know the location of the loads on the bridge, we don't know the load values, we don't know the parameters of the bridge. Also, we can measure the acceleration response of the bridge to this traffic, and we can synchronize it with the cameras. So we have the acceleration response, we know the location of the loads that are passing on the bridge, we don't know the load values as properties of the bridge. So we can set up basically load and parameter estimation model updating problem for this. Well, this was an SBIR project. Before joining UNR, I was in a company, we started this, and when I joined UNR, we continued this. There is a 4 years of development between what I'm showing you now and next slide is that we went through verification studies, validation study, and experimental setup. I'm going to show some validation study in real-world settings to show how this thing works. So for real-world testing, we actually wanted a bridge that is wore out. We went to Nebraska. In Nebraska, there are 3 bridges that are wore out, and DOT of Nebraska is giving them for research. So we used all the 3 bridges. I'm going to show the results of one of the longest bridges called West Utah Bridge. We went into the bridge, we installed some wireless accelerometer sensors to measure the vibration data. The point of wireless to have something plug and play, something that we can easily install and then disconnect. There was no traffic camera, so we came up with a very simple camera system, including Raspberry Pi and some tripods, and we put many of them along the bridge so that we can have the field of view of the whole deck of the bridge. And it resulted in something like this. As these different cameras are seeing the vehicle, we are processing the data, we are projecting it on the coordinate system of the bridge, so we know the location of the vehicle on the bridge as it's traversing. Very good. So we did that. Now we need to develop a model because we want to do model updating. So actually developing models of these old bridges is not trivial task. So this was a steel deck bridge, so steel girders with concrete deck. And we were very interested in delamination in the deck. We wanted to see how much delamination damage we have in the deck. These old bridges actually have a lot of situation boundary condition issues, like how we're going to model. There were some pin and hangers. There were some supports that we don't know how to model them. So actually we needed to invent what we call a two-step finite model updating method to deal with this problem. Basically, with the first step, we fixed the boundary condition of the bridge, and the second step, we estimated the parameters that we want to estimate. Okay, so we took care of the model as well, and these are some validation results that I'm going to show you. So this on the top shows the vehicle as it's passing on the bridge. We have the accelerometers installed in this black dot location, collecting the data. Through the model updating process, this shows the model updating process. We are estimating the vehicle load. It was a single truck, so it's time history of the vehicle load as it's passing on the bridge. The parameters that we wanted to estimate is the effective elastic modulus of the deck, because that can be used for estimating delamination and degradation in the deck. So these are the effective elastic modulus, the evolution of the effective elastic modulus of the deck across 4 different segments of the bridge. And at the end, you see some comparison between the measured data in green and the data that our updated finite model is saying in black. So basically, the model updating is trying to basically reduce the discrepancy between the model prediction and measurement and extract information through that process. As you see, there were some good, the discrepancy is reasonable. So this is the most important thing that we can use for damage detection. This was our bridge. We had 4 spans in this bridge. This was the estimated parameter. If you put it in the perspective, it's something like this. This is the effective elastic modulus of the deck. Again, it can be used for damage identification, for delamination and degradation. And based on the literature, basically we concluded that we have severe deck degradation in span 2 and 3 and less in span 1 and 4. But this is not validation. We had some other sensors, strain gauges that we use for validating our model updating, but for this specific bridge, we had ND data. So these are ground penetration radar. ND data are used for basically deck delamination, detection of deck delamination. Now, comparing ND data with effective elastic modulus is not possible. This is very mishy-mashy thing, but we came up with a method to qualitatively compare basically the amount of degradation here that we get from the NDE with the effective elastic modulus that we are estimating. Actually, NDE was telling us that we have more delamination and degradation in span 2 and 3, and we got the same thing from our model updating. So it's a proof of concept, or a validation, if you will, of a prototype. Now, I want to quickly jump to another application, very quick, before going to model updating, is offshore wind turbines. Again, we had the opportunity of instrumenting one of the wind turbines in Block Island. Block Island is in Rhode Island, East Coast, United States. There are 5 wind turbines there. My colleagues had the opportunity, not myself, to instrument one of them, so we wanted to start doing that. The big problem here is that we want to install some sensors on the pole, estimate the wind load, and then use that estimated wind load to predict the remaining fatigue life of the pole and connection and so on. So that's basically a problem statement. But the question is now, where should we put? The question is question of data. Where should we put the sensor? What type of sensor should we put to be able to do that? So we went through a very comprehensive, what we call identifiability analysis, or optimal sensor placement, to understand where we have to put our sensors to get the information that we want. I'm going to skip the details. Basically, there are some details with numerically simulated data. After that, we went instrument the actual wind turbine, one of the wind turbines in Block Island. We collected the data, and we could do wind estimations. So these are the estimated wind loads that we have, and these are the comparison between our measurements and updated model response. As you see, the updated model response and measurement match reasonably well, and we are estimating a wind load that was also cross-validated with wind speed and so on. It's reasonably well, but of course there is no ground truth. We don't know what is the true value. So this is an estimate. Okay, now let me talk about, I show these examples to show you the power of this method and the application that it can have. But of course, it has like any other method, there is no lunch for free. There are weak points in it. The biggest weakness that we have in this model updating method is what we call modeling error, or model form uncertainty. is that when you generate your model, there are always variations or error in mass, in how you characterize damping, how you characterize the unbalanced internal resisting force, and even external loads that we are not measuring. So how can we deal with these errors? If we don't account for them correctly, our model updating result would be biased. I'll show one example next. One idea is that we're going to collect all the sources of error or uncertainties and lump them at the structural level in an error or noise vector. This idea is not new. It's called Kennedy-O'Hagan back in 2000. Proposed this idea for stochastic simulation and so on. The novelty that we have here is that we're going to estimate the higher level statistics of this unknown noise along with our parameters. I will show how. So basically now our problem is that when we have this model updating process, if we have modeling error, the simulation error, which is the difference between our model prediction and measurement, cannot be modeled as a zero mean stationary Gaussian white noise as you have it here. It becomes actually a non-stationary, probably non-zero mean noise with probably cross-correlation between all your covariance matrices. So really the problem is that we want to now estimate not only the probable distribution of our parameter, but the mean vector of the noise and covariance matrix become also random variable, random matrix, and random vector and random matrices that we want to estimate the higher level statistics. So that's what we want to do. So solving this maximum a posteriori estimation problem, if you want, is mathematically challenging. My student has been working. The novelty is that we expand this to a case that we want to estimate not only the parameter, but also the input and the higher statistics of the noise. I'm not going to go through the details, but basically solving this maximum posteriori estimation problem is challenging. We came out with the fixed point iteration method to iteratively solve this and estimate the higher level of statistics. Let me show you with an example. So let's do a very, very simple example. We have a 5-story building. Let's suppose that we have sensors or accelerometer installed on each floor. We are measuring the acceleration response. We don't know the input ground motion, and we want to estimate, very simple, elastic modulus and Rayleigh damping parameter. Intentionally very simple problem. Here we are assuming that we have a non-zero noise and a noise that has a covariance matrix that is time varying applied on each of these sensors. If you want to see how the realization of that noise will be, it will be something like this. If we don't do and these are the parameter estimations. So 1 means true value, right? It's the numerically simulated data. If we don't treat the modeling error, this is what we get. Basically, all our parameters will be biased. They don't converge to 1. They converge to some bias value. That's what we call bias estimation. But when we treat the modeling uncertainty, then all your parameters will converge to true values. And if you want to see how your input motion will differ, this is the case that we have a non-adaptive case, and this is the case that we are treating with the modeling error. So you see that you are improving the estimation of your input. This is numerically simulated study, so it's just to show the concept. I'm running out of time, but there is another idea that we are working on, and this is applicable to nonlinear systems. In a nonlinear system, when you have this hierarchy of nonlinear finite element model, right? You go from structural element to structural level, element level, integration point level, you have material. Oftentimes, this material form that we are defining is a fixed form. We're defining a fixed form for concrete, for example, for steel, but your real material doesn't behave like that. So the idea here is that we want to account for these differences. We can actually define a machine learning component inside our material model to learn that errors, sources of error. We call this idea machine-infused physics-based model updating. Or you can, all together, you can say, learn your material model through a machine learning. And one quick example, and this is very simple example. Of course, when we come up with new idea, we always test it with simple example. This is a ground through the structure is a mass spring with springs that have bilinear behavior. These are the black lines. And we are trying to basically replicate this system with a system that all the springs have a machine learning, a recurrent neural network. And we are generating some data. We want to learn this recurrent neural network, and this is how the model is learning. The blue black is the true ground truth, and the red is what machine learning has learned from the material model. As you see, there are some discrepancies, but overall it's doing a very good job, and the responses are matching. So I talk about model updating, show you some example. We'll talk also about the challenges of modeling error, which is very real, and I show you two methods to deal with that. I think I exceeded my time. So now getting my moderator hats on, I think we have quick time for maybe one quick question, and I will be happy to be available after the talk to answer your questions. Yes?
Got a quick question.
Yes.
You're probably aware of the work that Chuck Farrar did on Ebrahimian.
Yes.
And everything you've shown here, stationary in the system is implicit.
Yes.
And we found for significant damage they induced, the change in the bridge dynamics were less than the diurnal variation.
Exactly.
So how do you think about that?
So let me tell you what they did. So they had a bridge. They basically installed sensors that collected ambient vibration data. And the bridge has a lot of significant loss in the pre-tensioning force.
Yeah.
And then they did that. They checked that the modal properties of the bridge is not changing. And then they cut the bridge actually, and they saw that actually there was a lot of loss in pre-tensioning force. What we are doing here is different.
But they had diurnal variation in the bridge dynamic properties due to the sun hitting on the
Yes, environmental effect is very important.
And you haven't addressed that here. How do you think about that?
So let me answer the first one first, and then we'll go to the second one. The first one is that over there, that's ambient vibration and modal properties. Modal properties will not change. But when you have vehicles that are passing, there are a lot of localized effects that will show signatures in the process. And we have done actually a test with the pre-stress gear there with the loss of pre-tension. So we show that that can be done. On the environmental effect, that exists because we were talking about the technology. So our solution is that if we're going to monitor a bridge, we're going to monitor it like at the same time of the year, so that the environmental condition is
In the same time of the day.
in the same time of the day, or yeah, something like that. Like if you want to monitor the bridge
you're
at
forcing
noon,
it to be non-stationary by observation.
because we want to compare things, right? But environmental exists. We don't have a good solution for that. So we have to move to our next speaker. If you want to thank me.